Hi, my name is Mitali Gupte, and today I will be discussing my results from Lab 3, which consisted of finding the mass of a black hole. In this lab, I created a computational model of a star orbiting a black hole. The star's trajectory was calculated using my email address as a seed. Using the star's motion data, I calculated the gravitational net force acting on the star, and from there, I used the net force in the star's position and mass to calculate the mass of the black hole, which I found to be 9.24759 times 10 to the 33rd kilograms. Here are some initialization conditions for my model. I assigned the star as the system and the black hole as the surroundings, where the only force acting on the star is the gravitational force of the black hole. My timestamp is 86,400 seconds, or 1 Earth day, and the mass of the star is 2 times 10 to the 30th kilograms. The fundamental principles I utilized in this lab were the momentum principle, Newton's second law of motion, and Newton's law of universal gravitation. The first equation represents the rate of change in momentum, which is equal to the summation of its parallel and perpendicular components. This equation also represents the total net force based on Newton's second law. Next, I have the formulas for the parallel and perpendicular components of the net force. The parallel component of the net force points parallel and in the same direction as the object's motion. The perpendicular component points perpendicular to the object's motion toward the center of the kissing circle. I used Newton's law of universal gravitation to find the mass of the black hole. This principle describes the force of gravity acting on a pair of objects which is dependent on the object's mass and inversely proportional to the distance between them. To calculate the mass of the black hole, I will set the force of gravity equal to the net force of the computational model and solve for the black hole's mass. Here's what my computational model looks like. The black sphere is the black hole at the origin and the yellow sphere is the star. The arrows represent parallel and perpendicular net force respectively. As you can see, the forces grow exponentially as the star approaches the black hole and shrink back down when the stars get further away. This is reasonable based on Newton's law of universal gravitation. As the distance between them decreases, the forces will increase by a power of 2. Here you can see the initialization conditions of my code. For the components of the star's velocity, based on the position vector that was created using my email address as the seed. This part of my code is the most important. Here I go through the steps to calculate the net force and its components from the position of velocity of the star's motion. I set initial and final momentum equal to the mass times the initial and final velocities. I then found the change in velocity and the change in momentum. Next, I implemented the momentum principle and found the rate of change of momentum to be based on Newton's second law. I set Fnet equal to the rate of change in momentum. Here I calculated the parallel component of the rate of change in momentum by multiplying the magnitude of the rate of change in momentum by the initial momentum unit vector. I then set this equal to the parallel component of the force and used subtraction to find the perpendicular components. Once I found Fnet for all my data points in my model, it was time to calculate the mass of the black hole. Again, I used Newton's law of universal gravitation, but I solved it for the mass of the black hole. I used 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared for the gravitational constant. Through this process, I found the mass of the black hole to be 9.24759 times 10 to the 33rd kilograms. Here are some follow-up questions. What does it mean? How is the net force different from the rate of change in momentum and its parallel components? Well, essentially, net force is what causes the change in momentum numerically. They are the same. However, the net force causes an acceleration, which is a change in velocity. Therefore, what causes a change in momentum, so net force is equal to the rate of change in momentum, but they are not the same thing. What if the black hole was swapped out for a different black hole at the origin? If the star's motion remains the same, it would be impossible to find a different value for the mass of the new black hole. In this lab, the star's motion is predetermined and not based on the gravitational net force of the black hole. Basically, the star's motion decides the mass of the black hole, and if that does not change, then neither will the black hole's mass. Thank you.